Self.
To sell.
Yeah! Hey everyone, welcome back to Cells to Sell. My name is Heem, that's Nick, and with us today we have Tesh Pierre. How you doing?
Hey man, it's nice to meet y'all.
So today we're actually really excited to have you on today because you're a PhD student who's very passionate about letting other people know what you want to do, what you're doing and everything, and yeah.
Yeah, so just start off with a background. Where are you from? Where'd you go to high school? Like, how long have you been at Case? All that kind of stuff.
Sure, yeah. So I was originally born and raised in the Bahamas. I went to a nice Catholic private high school there that really set my trajectory towards where I am now. Then I went to Florida for undergrad, did my undergraduate at Florida Polytechnic University, a very small STEM school in Central Florida. I got my BS in mechanical engineering from there. And I got involved in a lot of stuff. I started doing some research while I was there as well. I was working in a solid state chemistry lab, so that was like kind of my exposure to like science and like doing research, the type of stuff that I always saw on TV.
Were you in the lab all 4 years of your undergrad?
3.5, yeah. I started my second semester freshman year.
That's pretty good.
Yeah.
So that's really rare. It takes a while for some people to get into labs.
It does.
I didn't get into a lab until I got here at Case in my graduate school.
Yeah. I was very fortunate. The friends that I had that were older than me pushed me towards to do research. It's like, find a professor that you like. And I took my professor's class my first semester. It was a chemistry course. I liked him. I was like, hey, I would like to work in your lab. And second semester, we got started.
Were your other older friends also mechanical engineering?
Yeah. They were mechanical engineering. They were a few years ahead of me, and so they already started their research.
That's awesome.
And then you transitioned to medical because Case is a very medical-oriented institution.
Yeah.
Do a lot of innovation and stuff with all kinds of areas of science, but they do it in medicine.
So the way that happened was that based on from all the research and stuff I've been doing, I knew I wanted to do grad school, but I wanted something that's interesting enough that I can spend the next 5 years in, and so I was racking my brain trying to figure out what to do next. My mentor, he's the one that actually recommended that I take a look into biomedical engineering, and I was like, oh, that's weird. I haven't done anything biology related. So I looked into it. I saw a lot of mechanical engineering principles and stuff being applied. And so I did a summer research in undergrad experience at Johns Hopkins in a biomedical engineering lab. And that was my first exposure to BME. And that's when I knew, I was like, yeah, I'm definitely doing BME.
That's cool.
Damn. Johns Hopkins.
Yeah.
Undergrad. That's crazy. That's awesome. So what are you doing now? What are you getting your PhD in? What are you pursuing?
Yeah, so now I'm a fourth-year PhD student. I the biomedical engineering department. My research mostly focuses on cardiac tissue regeneration. Yeah.
Oh, wow. So are we talking like organ on a chip on an organ, or are we just growing them in culture?
So my lab does do some chip work, but for me in particular, I'm looking at using biomaterials as a therapy for patients with heart failure, specifically looking at extracellular matrix-based material and delivering those in a variety of ways to help the heart to regenerate.
That's incredible.
So are we talking like medical devices, so like the interface between a medical device and your heart tissue? Like, is that biomaterial, or are you talking about a stem cell kind of therapy?
So this type of stuff I'm working with, a stem cell can be incorporated into it, but for what it is now, and from what I'm doing, is just a hydrogel that can be injected inside the infarcted heart, and then it's going to have all these there's soluble factors that are released from the hydrogel itself that then has these downstream therapeutic factors.
Okay, hold on. Back up. So you have basically created this hydrogel. Or you built it off the shoulders of giants.
Right. Yeah.
But this hydrogel, okay, what's like the process? So when you inject it into a heart that's undergone some heart failure and some damage, what do you in the perfect scenario, what does your technology do?
Yeah.
Oh, so to help answer this question, I think understanding where the material come from will kind of help.
Okay.
So we use decellularized extracellular matrix from hearts, specifically from pig hearts.
Okay.
What my lab has found is that the age from which you get that extracellular matrix, the age of the animal matters. So a neonatal heart versus an adult pig heart. And so we find that the neonatal heart, when you decellularize it and you break it down through all these enzymatic reaction and make it into a hydrogel, when you deliver that fetal ECM to an injured heart in a mice, it actually has there are greater therapeutic effects in comparison to its adult counterpart. So the idea is that in the fetal stage of development, by the time the pig or mice or mammals in general, by the time they got to within a week, the composition of the heart is completely different from what it was in fetal. So the idea is that there may be factors in the fetal heart, as is, in terms of what it's composed of, that can promote regeneration or cell growth. And so we take that decellularized matrix, deliver that into the injured heart, and I guess the ideal scenario is that the cells will respond to these signals that are found in the fetal extracellular matrix. So the cardiomyocytes would want to proliferate, which in the adult heart they typically don't, or it's incredibly low. New blood vessels will want to form. The fibroblasts won't produce as much scar tissue, and so you have better recovery.
I was going to say, it sounds, taking cells from a neonatal mammal, just in general, even if you're not talking stem cells, you're still talking about all of those growth factors and all of those proteins in the extracellular matrix that might be able to bind to a surface protein and maybe cause a downstream event for adult progenitor cells to be kicked back on. Exactly. I think that's really cool. And it's something that a lot of people tend to forget is, the heart is a muscle. There are still going to be, they're made of different types of myocytes, but there are also, muscle stem cells still in there that might be able to be activated. So I think that's super, super cool. I would have never.
So
man.
Why is it called hydrogel? So hydrogel, is it because it's just a gel-like substance, kind of like just feels like a gel?
Yeah.
It looks like a gel? Yeah,
so the hydrogel is the final product. It's called a protein suspension when it's in the liquid form. But when you inject it under physiological conditions, it actually gels. So you start to have these covalent cross-links that start to happen between the proteins, and then it kind of forms a solid gel that kind of anchors itself at the site of injection.
Oh, so this has to be pretty invasive if you're talking about the heart, right?
Yeah.
Right.
So are you going into the chest cavity, like through a rib, between the ribs or the intercostal space, or is it more of like an IM injection?
We cut the chest open and then we directly inject it at the site of where we ligate the coronary artery to cause an infarct. So we do the injections there. There have been some clinical trials, not by us, but people that are using other types of extracellular matrix base materials. There's been some early efficacy studies, safety and efficacy studies, where they actually use a catheter. And then they go in and then they go past the valves and then they inject the ECM to the myocardium through there. So that's an option as well. That way you don't have to cut the chest open.
I was going to say that if this product were to ever go through the FDA approval process and eventually find its way to humans, I think that would probably be the more preferred way of what's the word I'm looking for, of administration.
Yeah.
Right?
Yeah.
So I wouldn't want my chest cut open for open heart surgery for hydrogel.
Yeah.
But, we go through the calf all the way up and the leg through the hip. And I think that would be a great, even in the ER, you could push that in probably an hour and save some lives. I think that's incredible.
Yeah, and that's a pretty interesting point. Recently I discovered, not discovered, but in talking with some physicians in the field, the patient population that you're looking to treat matters. If the patient, let's say, has an ejection fraction around 30 to 40%. While that's not ideal, it's not enough for surgeons to go and cut them open. So you can't use an invasive therapy in that. So ideally, you want to couple it with a therapy where the physicians already have to go in, maybe with a catheter, and then you can include it in there. And then the other extreme side is that by the time the patients get heart failure and they need heart transplant, and maybe they're on a left ventricular assist device, that patient may be too far gone for the therapy to have its full effect. So that's another side of the research that I'm starting to expose myself to, is like, okay, we can do all these fancy stuff in animals and the craziest things with animals, but when it comes to human, we have to make this practical that physicians are going to want to adopt.
Absolutely.
So wait, let me ask you a very technical question. If you, let's say, put this hydrogel through IV, do you think there'd be off-target effects if there's another injury in your body? Or is this very specified to cardiac injuries or muscle just injuries, because you did get this from pig
Right.
cardiac muscle, right?
Right.
So does the healing happen in the body for non-muscle tissues, or do you think it would happen only for muscle tissues?
It would be a bit difficult to tell that. I think there will still be some off-target effects, but will it be adverse? I don't think it would, because remember, what's being delivered is extracellular matrix. All the cells in the body are pretty already used to it. It's not like it's some synthetic drug. So if we take a component from it, like collagen, if collagen goes to the skin, doesn't really damage things, skin already has collagen. But a systemic delivery like that may reduce the dosage that gets to the heart. But some of it may still get to the heart and may still have some degree of therapeutic effect. But in terms of like off target, it being in circulation and going through your body, because these are natural biomaterials that the body's already used to, they'll just break it down normally and then just go down away.
Yeah, and have there been any thoughts with this extracellular matrix? Have you guys done, I'm sure you've done extensive testing on what is actually in that matrix. I'm sure you have. Is there any concern of like an oncogeneous event where you put this hydrogel in, but you might see, little polyps, little tumors on the heart because, something might have been a little overstimulated?
For sure. So one thing that might be, there may still be some genetic materials that are stuck inside the ECM itself. During the decellularization process, it's not entirely perfect. There is a minimum amount that they require. I don't remember off the top of my head, but you can do some staining for nuclear materials and then see how much is in there. So if there's too much left, so there may be, I think inflammation is more of a concern than any type of tumor cell formation. To my knowledge, I personally don't think that with the ECM therapy that there is a high risk of that.
Just typical. I was just wondering.
What's the risk for immune rejection, because these are coming from pig? So is the studies right now happening from pig to pig or pig to human?
Yeah, so a lot of the studies that we've been doing has been across species. So it's been a xenogenic transplant from a pig heart to a mice. The clinical trial that I was telling you all about, it was from decellularized pig heart to a human heart. And so the thing that's most responsible for causing these adverse immune effects is the genetic materials that is found in the cell. So if the proper decellularization protocol is followed, ideally there shouldn't be that much of an immune response. However, the proteins do differ from species to species very slightly. But so far from what we've seen, that hasn't been that big of an issue. But it may very well be that as we get to larger studies and as we do much longer studies as well, because right now we're looking at what's happening with the acute injury, and we want to see improvement in heart functions within a month or 2 months. But as you go much longer, there may be some adverse effects that we haven't even seen yet.
Yeah, that was my next question is, the length, if I have a heart attack, or something happens and I get your hydrogel, am I all of a sudden dependent on your hydrogel now? Do I need to get it once a year? Do I need to get it every 5 years? Just to make sure that my heart's staying healthy? Or is it kind of a supplement? I get it once or twice, and then it's just like, start dieting differently, work on like your cholesterol levels or something, and I think that would be one of the questions that I would have if I were going into this study. So how far out, you said you're in your fourth year?
Yep.
Or your fourth year? So have you been this has been your project for 4 years?
Yes.
So what is the next step for you? Do you plan on, continuously working on this, maybe stay at Case, kind of try to perfect this art of this hydrogel, and then, kind of do a spin-off? Or do you think you just kind of want to get some papers out, maybe teach, or, my question is, what's next for you? What do you see yourself doing next?
Yeah, so I like the extracellular matrix work that we do in terms of for kind of finishing and completing my PhD. It would probably be more centered around looking at better ways of delivering the hydrogel. So one of the challenges right now with high hydrogel delivery in the heart is delivered as a suspension, and when it gets under physiological conditions, then it gels. But there's some loss because the heart is a very dynamic environment. So there's a lot of pumping going on, there's a lot of moving going on. So there's probably some loss. And then if the gel's not sturdy enough, because there's enzymes already in the body that naturally degrades this material. So one thing I'm looking at, okay, how can we then extend the therapeutic window, essentially. So one paper that we recently published last year was we delivered the hydrogel as a microparticle. So it's already a solid, and we deliver it through the same method with the syringe. And so with the particle that we have, increased therapeutic effect because one, it's already a gel solution. We've reduced some of the loss that happened, and it's going to take a longer time for it to degrade. So that's more time that it's in the body and that these soluble proteins are being released to have the therapeutic effect.
It's a big challenge too, especially working in the heart environment.
Yeah.
Because, we always think about liquid cancers and like lymphomas, myelomas, all that kind of stuff. And we think about it as almost like a solid tumor. Like you picture it in your mind, you're like, okay, this is what it is. But they're moving so fast throughout your body. So trying to get a hydrogel to stick in the heart, that seems like a pretty big challenge. And especially trying to hit a therapeutic window, especially when you're just trying to get there.
Right.
But I feel like some heart attacks occur on the vascularization on the outside of the heart. So the heart's own blood supply, right? So are you focusing on the internal chambers of the heart and the damage that is done there during infarctions, or are you looking at the heart as a whole?
So I think looking specifically at the former. So a lot of the injuries that we induce, so when you ligate the coronary artery, that's similar to a patient that has an occluded artery, which is I think how most of these injuries happen. So it stops the blood supply to the heart, and it starts to affect the outside wall first.
Well, it affects everything, and it affects how it pumps. Physically, how it pumps.
Right. So as time persists, a lot of what we're looking at is still at the acute phase. So the animal is injured, and they get the therapy within a week. A lot of studies I've looked at, they've been doing it within a week, whether immediately, a few days after, or a week after. So that's still pretty acute. A lot of these negative effects that happen in humans takes months and sometimes years of the heart constantly experiencing that load, and it trying to compensate for that load, and so then it starts to form the scar tissue to maintain the mechanical integrity of the heart. So those stuff kind of take longer and longer to form and things like that. But
So are there any plans to do an extended mouse study and a mouse harvest to look at those long-term effects? I mean, let's say you get 3-week-old mice, you work with them, let's say at 6 weeks, you cause a heart failure, insert the hydrogel, bring them back, and then you just let them live. And you just see, and I really like those graphs that we'll see in papers where it's 100% to 0% for you, it would be 100% 0%, and then days, and then you watch the line fall as they do. And I think that that's a really, really good figure that can summarize a whole study in just one thing, just by saying this drug or this treatment caused this many things to die in this amount of time compared to if you were to just take a control group and also like a naive group who has nothing done to them and just say, hey, this is the naive group. We saw a specific amount of advantage through our hydrogel. I think that would be really cool.
And I think that's definitely the direction a lot of people that are doing work in the cardiac tissue engineering space are trying to go to. Is like, okay, let's move from more of an acute injury to more chronic. Let's have these animals go under injury for maybe like a month or so, and then going with the therapy, and let's see, can we have similar therapeutic effects or at least some improvement? Because when you deliver it early, there's a lot going on right after injury, especially when you think about inflammation, and so all these cells are coming in, they're producing all these molecules, everything's being broken down, rearranged, cells are proliferating, etc. But after that injury stabilized, which is about for the 4 to 5 week time point in the murine model, once that injury stabilizes and you just have scar tissue, then can you stimulate a similar regenerative effect? So that's certainly what we're moving towards. So, and I think that we're going to find that we're going to have to come up with new exciting strategies to address that problem as well.
So,
that's really cool.
You know how you mentioned fetal extracellular matrix is different than adult ones, and the fetal ones are better? That same concept, basically, do you know Arnold Kaplan? He's a researcher here at Case.
I've heard the name. Yeah.
Many years. He's pretty much the father of stem cells is his name here. Okay. He developed this product, and since 2014 it's been considered a tissue and cellular-based product. But he takes placental tissue, and then he'll combine them with extracellular matrix and growth factors, and he makes this little gel kind of looking thing. And you can literally put it on top of anything to regenerate it. And he's had it fully covered by Medicare now for things like diabetic foot ulcer, for things like tendon repair. You can literally take a tendon out of somebody, wrap it with these stem cells because they're placental tissue, and the extracellular matrix, so it helps growth, and then the growth factors obviously to help the growth too. And then you can put it back in, and then this blanket literally just grows back everything it's missing. And that's extracellular matrix is huge for that. Now you just made that connection to me, because I was I've seen extracellular matrix be used before, and I didn't know that they have a lot of these factors that mainly are used for the connective part of things. Yeah,
for sure. And each organ and really each tissue has their own unique composition of extracellular matrix. So if I take a complete stem cell and I put it on some heart ECM, it may differentiate more towards a cardiomyocyte, versus if I put it on some skeletal muscle ECM, it'll differentiate more to skeletal muscles. So it's actually, there's a lot going on in there in terms of growth factors, even just from the structural ECM themselves to collagen, the type of collagen, how they're arranged as well. So with muscle, you have these striations that are happening that can induce a certain cell phenotype as well. So yeah, it's pretty important.
And your work probably deals a lot with microenvironments, right? Because microenvironment for every different cell type is so different.
Right.
So what microenvironment work are you familiar with and have researched about cardiac cells in general?
Right, so a lot of the preliminary studies that we do in the dish is essentially trying to tailor the microenvironment. My lab has looked a lot at it from a mechanics standpoint. So as you have cells on substrates of different stiffnesses, how does that affect the way cell behave? So with some of the cardiac fibroblasts that we're looking at, If you have it on a stiff substrate, that may promote it to differentiate more into a myofibroblast, so it's producing more of these connective tissue, more of these collagen fibers that's forming the scar tissue. In certain scenarios, that's great. Like if you get a cut on your skin, that's great. You need it to form a lot of scar tissue so it can heal. But in the heart, not so well, right?
Okay.
Yeah. But we look at it a lot from the mechanical environment, and we've even done it in vivo as well. So tailoring the mechanical properties of the heart, whether softening it or making it stiffer, and then seeing how our therapy works from there as well.
So in the lineage of like so stem cells and then myocytes and cardiomyocytes and that it's very specific thing, there's a difference in ECM between a more scar tissue like myocyte or a more soft myocyte, and like how specific does it get? Like, do you know what I'm trying to say?
So with the ECM itself?
Yeah. So like, is there like only a 2 protein difference between something that'll turn into a scar tissue versus something that'll turn into a soft tissue? Like how specific does it get, or is there a wide range of cardiac proteins?
There's a wide range, but the one that we usually point to is usually like with the scar tissue is usually a ton of collagen 1 that's being produced. In the heart, there's a natural balance between the amount of collagen 1 and collagen 3 that helps it remain maintain its tensile strength, but still has the elastic nature as well. But with the scar tissue, when it starts to produce just a ton of collagen 1, then you have a more rigid structure. Yeah, and the cells are going to respond differently to that. As that starts to form, the cardiomyocytes may undergo hypertrophy because they're trying to compensate for the lack of compliance of that part of the heart. And then eventually it leads to some adverse effect further down, because that's going to affect gene expression and all that stuff.
Yeah, I just think this is incredible. This is so cool. I mean, this stuff is so interesting, and all the different applications it can have in the future, not just for the heart, but just like we could talk about hydrogels and liver failure. That kind of stuff.
Yeah,
and I'm sure that's being done already. We could talk about
right.
lung cancer and lung failure and all that. And it's just very interesting. Though I just have one more question for you. So when you guys take that hydrogel, insert it into the heart, let them sit for 1 day, 2 days, 5 days, 7 days, what testing are you doing? Are you taking out the heart, or what are you looking at, and what are you looking for in that cardiac tissue? Right.
So before the animals are euthanized, we do some functional analysis. So do some echocardiograph. We get some functional data from the heart. So that's actually a pretty big part of some of the work that we do. So we get the how much blood is being pumped out, how compliant is like the heart muscle. So we're able to get those just via ultrasound. So you could do it before injury, right after injury, right after treatment, and then after a longer time point. I think we went out to about 31 days, where in the mice with the infarction and no treatment, you just see the heart function just start to decrease. Whereas with the one that get treatment, you see an improvement over the disease, and an animal still doesn't get to where a healthy mice is. So there's still a lot of room for improvement in that aspect.
That's super cool. That's super cool.
Have you used induced pluripotent cells in your lab to run any studies yet?
So I am actually looking to use them pretty soon. I don't, but some of my lab mates do some work on that. We've differentiated the iPSCs into cardiac fibroblasts as well into cardiomyocytes as well. So that's some of the next phase of some of the stuff that I want to do. I want to go deep down more into like what's happening at the cellular level when they're exposed to these
environmental factors.
Yeah, exactly.
I can't imagine how cool would it be. You know, you look at a tray under some electron microscope, and then you physically do something to it, and like, can you see them change in real time, or do they take like minutes, hours to turn into that cardiac? Because if you give it mechanical stress, it'll turn more into a cardiac or tissue or muscle tissue.
Right, yeah. So some of this stuff happening over the course of days and sometimes weeks. Like example, to get the iPSCs to differentiate into cardiomyocyte, if I remember correctly, I think my lab mate, it takes about like 20 days for that to happen. You have to feed them certain things. There may be things that you can do to make that process more efficient, because that's just in the dish. Maybe you want to put it on some ECM, or if not hard ECM, maybe something close enough like collagen that's a little bit more compliant than just a dish. You could modify the surface of the substrate that you're putting in. If you put on, modify not only the stiffness, but if you like put some grooves in it, maybe the cells are aligned, and that may promote a more mature and a more cardiomyocyte phenotype. But yeah, it can happen over the course of a long time. But in real time, because the cells are contracting, you may be able to see some changes. So something that we do, so if the cell may be diseased or so, you can give it something like caffeine, and then you can look at like the rate of contraction. Like you may expect that a cell that's diseased may not have as much contraction. We even measure the force of contraction as well using something called traction force microscopy, and then you can see based on a healthy cell versus a diseased cell, how is that force of it contract? Is it contracting with the same amount of force? And then, yeah, there's a lot of the physical stuff that you can
really
look
cool.
at.
That's super cool.
And you mentioned how it takes 20 days, so that's just like the nature of doing a PhD, right?
Yeah.
You have to wait days, probably.
Yeah.
Weeks.
Yeah, some people need
For
weeks and stuff.
cells that might not even be ready, or they might be dead.
Oh, it happens.
You did something wrong on the 19th day, you're supposed to harvest on day 20, and something happened.
Happens way more often than you think.
So with your lab mates growing those pluripotent cells in culture, are they putting this into the hydrogel and injecting it in these mice, or are these just different studies?
So these are different studies.
Have you thought about that?
Yeah. So, well, no, there's only so much you can do in a 5-year period, but those are some of the stuff that I would like to test as well. So it's like, I know some people are looking at, so there's like 3 main therapies, in my opinion, for like cardiac tissue engineering. So there's stem cell therapy, there's gene therapy, and now extracellular matrix therapy is now popping up. I think there's a great advantage to using stem cell therapy and ECM-based therapy as well, if you want the ECM to affect the stem cells or affect the surrounding cells, while the stem cells provide some extra support that's there as well. Yeah, there's definitely space to combine those two together.
That would be really cool. Mm-hmm. That would be really cool. That's something I think you would do when you get your PhD, and if you stick in a lab. Absolutely. And you get your own lab.
Absolutely.
And then you get to hire your own goons to come in there and just be like...
So much fresh ideas, man.
It's never ending. It really isn't. There's always...
Would you be a PI one day?
Yeah, I definitely want to be a PI one day. I love the science. I love the work. I'm constantly getting new ideas, and it's like, I would love to live with this, but, I would like to have an army of students who are motivated and who wants to just discover the secrets of the universe, for sure.
Not only that, if you go into industry though, they'll tell you what to do, which you will still be in control of the research a little bit, but it's kind of guided for you. Versus if you join an institution, you get a lot of freedom because you have to write the grants and everything, but you guide your life. Right. So which one would you rather do? Because in industry, it's also a lot of cool benefits. You work with really awesome tech and with volume.
Yeah, I must say, it's a hard decision to make because I've toured some companies that are doing some incredible stuff and having access to the latest technology, that's amazing. But at the same time, I love generating my new ideas and be like, hey, I really want to see if this works. So I think I'll definitely be leaning more towards the academic side of things. The grant process that has to be some business own, but If you can get that to work out, you can do some pretty cool stuff. I love going to the talks when professors come and they give their talks and they're talking about the stuff that they do and with their labs, and especially the ones that are really established, and see all the different cool stuff that their lab are doing. It's like, yeah, we had this idea, so we just approached this. We got 2 students to just work on this project. I think that I love to jump from ideas, stuff like that. I think academia would be the best place for me to do that. To keep stimulating those brain muscles and just be like, hey, this new idea, I just want to work on it. Let's go. Let's see what's next.
And what are your most well-known labs here at Case for you? Like, which ones are your most popular? Like,
let's see. Well, there is the Sengupta lab in the BME department as well. He works. He does synthetic platelets. He does some pretty cool stuff. I love some of the stuff that we do because it's more like a targeted therapy, where the platelets he has are like targeted specifically towards that injury area to help with like blood clotting and stuff. I think that's super cool. The Von Rechem lab, also in the BME department, does a lot of drug delivery stuff, and they have their material as a affinity-based material, but drugs can also be reloaded in that, and so they've incorporated the materials, I think, in implants and stuff like that, and so you can think of implants if there's a lot of inflammation, you can do some anti-inflammatory drugs, and when those drugs are depleted, they can be re-administered again and
Reloaded.
find themselves in those pockets. Yeah. So
like sustained delivery. So if you put like an implant right here, if your knees are bleeding,
right.
you could put something because reloaded for a week, and then sustained release for a week helps you, and then you just do that.
Yeah.
Okay, that's interesting.
Yeah.
And they only stay in that device, right? They wouldn't circulate in your body, or like you're saying, these are circulatory things.
Yeah. So a lot of them are drugs that are like already on the market. That are already being used, that are already delivered systemically. This way, you may be able to have a more concentrated dosage at the site, exactly where you want it to be. Yeah,
Wow,
just a
that's
few
awesome.
pretty cool stuff.
That's awesome.
That's really cool.
Well, we've gone for 38 minutes now.
Nice.
So, probably 38, 37, 36, 38 minutes. So, I don't know. This was an unbelievable conversation.
Yeah.
flew
I actually
by.
learned quite a bit.
I learned so
I
much.
didn't know like ECM exactly what it had in it, and then when I heard hydrogel, that just confused me.
Oh, hydrogel threw me for a loop.
Oh, yeah.
Yeah.
I was thinking of like a steroid you like rub it on your skin.
Oh, like that,
Like a
yeah.
hydrogel.
Yeah,
But
yeah.
no, it's totally different.
Mhm.
And I think that the potential for your project is absolutely unbelievable.
Oh, yeah.
And again, this is coming from some stupid master student who just like loves ideas and doesn't really want to look at back them up. But no,
It's fun.
Science is fun.
Oh, it's fun.
We've said it multiple times on this podcast. Science is fun.
Mhm.
We need to continue to make it fun and have these, challenging thoughts that keep us pushing forward. And I think that what you're doing in your lab and what you are going to do, whether you decide to take your fun in academia or take the money in industry,
There's nothing wrong with either.
and there's nothing wrong with either.
You're
Right?
You're gonna
do
forwarding
great.
science in one
Yeah,
thing.
no,
You're gonna do great.
Yeah,
So,
as long as you get to do it, that's
all right. Well, we want to thank you for coming on this podcast. We really do.
Thank you all for having me. I say this is my podcast debut as a PhD student, so
Yeah.
I'll remember this for the rest of my life.
Hey,
We'd
so
love to
will
have
we.
you back
So will
on.
we.
Yeah,
And
definitely.
yes.
We would love to continue this conversation about just like ECM. Maybe next time we can review a few papers.
Yeah.
And if there's any papers that we attach to this, do you want to give the viewers a quick summary of what you
Just
made?
something like a review paper that's easy to read.
Yeah, there's this review paper, and I will share it with y'all. That I'm really, and we kind of talked about this. I'm really fascinated by the 3D printing space. So you can take a lot of these hydrogels and start to 3D
I was going
print
to ask
them.
that because when you
Yeah.
started talking about the hydrogel and you said something about placing it, and he asked about a device. I was always thinking like, is he talking like scaffolding or something with the heart? Like instead of using like a pig aorta, you go in with a 3D printed hydrogel
Yeah.
that almost like
fits
incorporates
in the shape.
or like you leave the damaged aorta in and like it almost like goes in and like fills all the gaps.
Oh, yeah.
And like makes it kind of healthy again, or like 85% rather than 100%.
Yeah,
And
these
that would
materials.
be awesome.
Yeah, these materials are like incredibly versatile. There's a lot you can do. There's a lot of chemistry you can do to these materials. Like you can make it do whatever you want. So if you want to make it 3D printable, and there's a review paper that goes over different ECM stuff and the stuff that they're doing with 3D printing, all that different stuff with cells inside of it as well. Very cool stuff.
So cool. So cool. So cool. All right, well, let's end it. We will have you back on.
Of course.
In in a couple weeks, a couple months, whenever you're free, because I'm sure you're very busy with your PhD. We totally understand. But we'd love to have this conversation again. And
for sure.
It was great to hear about your research, but next time, let's just sit here and talk about ideas, because I think it's fun for like-minded people to sit here and just think together.
No, for sure, absolutely.
All right, well, thank you guys for watching. This has been another episode of Cells to Cell. We would like to thank Mr. Pierre for coming on. He was great. He will be back on soon. So I'm Nick. That's him, and we'll see you guys later.
See you guys.